The gravitational wave in the cosmology is the kind new approach to address the unknown physics in the early universe. But before talking about the GW in the cosmological point of view, let's review the what is the gravitational wave in terms of the perturbations of the general relativity theory. One can expand the metric around the black space-time, whereas the perturbing metric is extremely small, and we can take the burst order in the h mu. Then we can obtain the linear orders of the crystal pair connections and the rich tensor and the scalar. And also from the linearized Einstein equations, we can obtain the wave equations with the choice of the Lorentz case. Then the H mu satisfies the following wave equations with the source term in the right hand side. And also we can choose the transverse and the trislash conditions for the H mu. So this is the transverse, and this is the trislash, so-called TT gauge. Then there are only the two degrees of freedoms remain. So the one polarizations that correspond to the plus, and the additional one is a cross mode. The important quantities in the gravitational waves in the cosmological point of view is the energy, or so-called the power spectrum, over the each Fourier frequency. There's some energies that deposited in the gravitational waves, and this can be described by the stress energy tensor T mu. This is the defined at the quadratic order in the metric perturbation. And in the TT case, the energy density is a zero component of the energy momentum tensor with the following form. The burst time derivatives of the h is ij. And we can plot the power spectrums over the specific frequencies in terms of the capital omega times the h scale, whereas small h is reduced to the Hubble. And this can be obtained by the logarithm derivativations of the energy density over the frequency f, where this frequency can be obtained by the Fourier analysis. And the many early universes which generate the gravitational waves gives a specific peak at the F star. So the energy spectrum get some behaviors. At the F star, it has a peak, and below this F star, the gravitational waves increases. I mean the energy spectrums, and energy spectrums are fall after the F star. In the expanding universe, the gravitational waves can be the part of the tensor perturbation part of the perturbing matrix. Here's Hij satisfies the TT conditions again. And if we calculate the Fourier modes and the polarizations, so here H is with the specific K modes, then each mode satisfies the following equations of the motions from the evolution equations of the density perturbation. In the absence of the source, the right hand side it shows these equations reduces to the damped wave equation because there's a Hubble friction terms with the expanding effect. And one important thing is the correlation functions between the perturbing matrix H's at the different between the different K mode. This is called the primordial tensor power spectrum, which is the Fourier transforms of the two-point correlation function. And if we assign the Dirac delta is on the right hand side, so we can obtain the tensor power spectrum PT through the K. This is open parameterized by the specific pivot scale K star. This NT is called the tilt or the power spectrum index, and AT is the power spectrum amplitude. One thing important, the quantity is the tensor to scalar latitude, which is the defines as the latitude between the amplitudes of the tensor perturbations and the scalar perturbation. These tensor to scalar latitude are important parameters in the impulations models and the constraint. Such a tensor perturbation remains some influence in the polarizations of the CMB at the approach of the recombinations and the ionizations. This produced the B mode spectrum in the CMB, the quantity C of the L. So because in the CMB polarization there are two patterns. The first one is the E mode, which is a gradient-like, and the B mode, which is the curl-like. And the pure E modes that comes from the some Haas part and the coarse part because it behaves like the divergence behavior. But the B modes that comes from the rotational structures. So the scalar perturbation makes the such E mode, but the tensor perturbation generates the both E and the B mode. So the primordial B mode in the CMB is the evidence of the tensor perturbation and thus the primordial gravitational wave. Such a B-mode components of the CMB can be quantified with the following statistical form. The CL of the B-modes comes from the following form. And here's a PT of the K is a primordial tensor power spectrums, and delta, capital delta B is the transfer functions connecting the tensor perturbations to observed polarization. So that this is a primordial one, and after the acting the transfer functions, now the observables are given by the CMB. In the BB mode class of the CL, there are two regimens, the low L and the other one is the large L. The low L is determined by the reionization and the recombination, but the high L is dominated by the gravitational lensing conversion from the E mode to the B mode. Recently, now that we can constrain how much the B mode in the CMB, for example, the Planck or BIZAP observations, the observed CLBB spectrum is given by the tensor to scalar latitude is less than the 0.03. This is a small value, and the pictures aims to the R to the 10 to the minus 3 order, so that we can test primordial gravitational wave from the CMB data. Now, the remaining time I'll talk about the primordial gravitational waves from the various early universals. If there is a cosmological phase transitions with the pulse load so-called FPT, then there will be the tube vacuum bubble inside of the force vacuum. So here's a tube vacuum, and this is a force vacuum. So potential has simultaneously tube vacuum, and by the quantum tunneling is the phase transition occurs. And the bubbles are expanded and they are collided with others, and this makes a specific sound waves or magnetic hydrodynamic turbulence in the plasma. And this analyzed eventually stochastic gravitational waves at some specific peaks in the frequency regions. As a model independence descriptions, the both of the pattern transitions can be characterized by the energy scale when the appropriate occurs, and the typical time scale, the durations of the phase transition. This can be represented by the alpha and the beta with the transition temperature T star. So this is a parameterization. Now the alpha is defined as the ratio energy density between the vacuums and the radiations at the T star, and this radiation advances given by the equilibrium thermodynamics, and the other parameters that are better durations that depends as the with the nucleation rates, the capital gamma. And there are additional input parameters like bubble wall velocity because the bubbles moves each other, and efficiency of backtest kappa, which describes how the vacuums the energy partitions into the plasma and turbulence. Also, all the phase transition proves the gravitational wave, and this can be represented by the specific frequency observed, but because there are cosmic expansion effects, the scale factors will be included. So under these characteristic frequencies are determined by the FOPT temperatures and the effective number of the relativity degrees of freedom G star at the FOPT approach. Similarly, so we can obtain the power spectrum in terms of sort of the frequency. So we can realize the gravitational wave power spectrums as the capital omega GW times the reduced Hubble H scale. Other possible source is a topological defect, which arises from the symmetry breaking in the early universe. The vacuum manifold has the non-trivial topology through with the degenerate vacuum configurations. The famous example is the cosmic twin domain world texture. And their evolutions become the source of the anisotropic stress as the obstagonism, and this generates stochastic gravitational wave backgrounds. Among these cosmic twins that were studied, they makes some string networks and makes the radiations forms of the gravitational wave. And also the dark matters and dark sectors can lead to the GW signal. For example, the primordial black hole as one candidate of the dark matter. This also can provide the gravitational waves. So far we talk about the positive gravitational wave source in the universe, but how we can detect the GWs and the current sensitivity is how much. The first one is the ground-based interferometers such as the LIGO. They are sensitive to the some specific frequency lines. Then other one is space-based interferometer like the LISA, which is sensitive to the signal from the massive black hole masses. And the other positive and the pulsar timing array (PTI), which monitors the pulse arrival timings from the milliseconds the pulsar. And there are diverse methods to detect the gravitational waves. The current detector has the limited sensitivity, so there is some omega GWs like the power spectrum, but the sensitivity is like that. And still the new gravitational detectors that are the direct measurements of the primordial gravitational waves. So we should improve the sensitivity to test the early universe model for the gravitational wave source. So the gravitational waves has rapidly become the central topics in the higher physics and cosmology, and this can provide sort of the fundamentally new observational window for the particle physics, and the current detectors that cannot reach to the power spectrums from the several model, but the future improvement can touch the testable sensitivities.